Hello, this is Matthew Van Prague, a sophomore statistics major, also minoring in computer science, and this is the video going over the material introduced for regression analysis sections 2.1 to 2.6, notably about simple linear regression and what this entails. To begin, we must understand some basic terminology. The textbook uses response variable y and predictor variable x. Since we are referring to simple linear regression, there will only be one y and one x for this video, although Chapter 1 said there may be multiple response variables or multiple predictor variables in a given regression equation. Firstly, each point on our dataset has a predetermined x value and a predetermined y value. Each of these observations can range anywhere on your graph, and the connection between specified points will determine how linear your graph will be. Of note in this chapter is how to measure the direction and the strength of both y and x, but we must first understand the correlation between the two variables. Our one assumption going into this is that y and x are linearly correlated, meaning there is some straight line relationship between the two. We must also know their sign and whether this correlation is positive or negative. We draw two lines on a graph, one horizontal and one vertical, to represent the separation points of the dataset given by standard deviation formulas for y sub I and x sub I. And these lines are known as y bar and x bar respectively. These lines can be found using direct equations. For example, y bar is equated by taking the summation of y sub I from I equals 1 to n and dividing that by the variable n. The same process is completed for x bar, except with an x sub I for the summation instead. We must then compute y sub I minus y bar, x sub I minus x bar, and multiply the two differences together, and this will lead us to the lines used to formulate four separate quadrants in our field. So like this, and these are our four quadrants. If the relationship between y and x is positive, then there must be more points in quadrants 1 and 3 than in quadrants 2 and 4. After you draw out the lines from y bar and x bar. Alternatively, if there are more points in quadrants 2 and 4 than 1 and 3, the relationship would be negative. The sign of the relationship is thus ascertained using the covariance of the quantity, which also refers to its sign. By using a formula for the covariance of y comma x, we can find the direction of the relationship, which is one of the two qualities we were looking for. If the covariance of y comma x is greater than 0, then there exists a positive relationship, but if it is less than 0, then the relationship is negative. However, although covariance tells us a lot about direction, we're still somewhat in the dark about strength, as the same graph can be used from a range of 1 to 10 as 1 to 1 million using this criteria, and we're looking for something that's more specific and lets us know direct parameters and our equations. To find the system's strength, we must standardize the data first. To conduct standardization, we must take each observation, subtract the mean, and divide the standard deviation. This gives us the correlation coefficient between y and x, which is better suited to the strength of the correlation. The overall correlation coefficient of y comma x is given by the formula 1 divided by n minus 1 multiplied by the summation of parentheses y sub I minus y hat divided by s sub y, close parentheses, multiplied by open parentheses x sub I minus x bar divided by s sub x, close parentheses. And this summation is from I equals 1 to n. An interesting property of the correlation coefficient, however, is that it is symmetric, meaning that the correlation coefficient of y comma x will equal that of x comma y. This is not true for the covariance we just looked at. Additionally, the correlation coefficient is useful in numerics, as it is clearly defined on a scale from -1 to 1. The closer the coefficient is to a limit, the stronger exists the relationship between y and x. For example, a coefficient -0.9997 would be an exceptionally strong negative correlation, and positive 0.9997 would be an exceptionally strong positive correlation. The correlation coefficient is still not flawless, though, as we can reach the case where correlation coefficient y, x equals 0, and this does not imply no correlation, but it can imply that there is no linear correlation. So there may be a quadratic correlation, or an exponential correlation, or no correlation at all, etc. But all we know is that the correlation is not linear. Furthermore, outliers are as stubborn as always and will greatly skew the dataset and affect the numbers for both covariance and correlation coefficient. The textbook offers an enticing example where there are 9 data points all in a straight line, and then a 10th data point way up here. So the so-called line of best fit ignores most of the lower down points to favor this one outlier. This is why it is important to check the graphs before making assumptions about the measurements, and examine a scatter plot prior to measuring the correlation coefficient. By examining a scatter plot, or taking the necessary precautions, we can eliminate the outlier from the equation, but this is still a flaw in the correlation coefficient formula. The computer repair data cited in the textbook takes these necessary precautions and develops a wonderful graph with a coefficient of 0.996, indicating a blatantly positive correlation, and strong enough conclusion that variable x and variable y are interconnected. However, the correlation coefficient is only used to measure the past and pre-recorded data points, and cannot be used to predict future points. We have no idea if future sales for a product will skyrocket or plummet based on this model. Moreover, we are only limited to 2 variables, x and y, and this model cannot be brought into greater dimensions. To rectify these inherent issues, we introduce regression analysis, outlined in section 2.4, which can both be used to predict future points accurately and can determine a model in more than 2 dimensions, while maintaining those desirable traits previously mentioned of strength and direction. Therefore, it is quite desirable in statistical measurement. The simple linear regression model is defined as y equals beta sub 0 plus beta sub 1 x plus epsilon sub 1, with beta sub 0 and beta sub 1 being constants or parameters, and epsilon representing possible error from the assumption that x and y are inherently correlated. The parameters determine the slope, and the coefficient beta sub 0 will determine the intercept, which we know is the predicted value of y at x equals 0. In this model, we tackle variables such as x sub I, where I represents the number we are dealing with, so x sub 9 would be the 9th instance of x in the model in numerical order. Regression analysis is different from the correlation analysis we previously described, as regression analysis takes specific concentration on the y variable and treats x as a predictor, which simply determines the variability of y, not the values themselves. This is different from our previous model, because that one weighed the importance of x and y equally. They were symmetric and interchangeable. X, y was the same as y, x. Also, unlike coefficient analysis, regression analysis will take into account the order of the variables. So, like I said, x, y will not equal y, x in this scenario. And this is a corollary from the lack of interchangeability. Using the previous computer repair examples cited by the textbook, we see beta sub 0 plus beta sub 1 multiplied by the units plus epsilon. However, how do we estimate the parameters, these unknown beta values, considering we need them in order to determine the entire linear model and the appropriate y value for every instance along the line. This introduces the important statistical tool of the least squares method, which measures the smallest sum of squares of vertical distance possible from each point to the central line. It is important to note that a least squares line will always exist, thus making it a somewhat reliable method to determine your parameters. There will be errors for this method, but we can reframe the previously stated formula so that epsilon sub I, which as we know represents the errors, will equal y sub I minus b sub 0 minus b sub 1 multiplied by x sub 1. And this is how we can account for those errors. We use formulas to find b hat sub 0 and b hat sub 1, and these variables represent the least squares estimates of their hatless counterparts. Thus, we can find a least squares regression line, which is an important tool in finding the strength of the tested line. For each instance, we can find fitted values, which are the points on the least square residuals line. Note the sum of the residuals will always be zero, thus making the least squares line a reliable comparison to the original line. This means that the sum of the least squares error above the line will equal the sum of the least squares error below the line. Positive plus negative of the same value will equal 0. There will be no positive or negative skew, and each point will be a direct translation on the x-axis that will equal 0 once all values of change are added together. It is henceforth implied that b hat sub 1, covariance y comma x, and correlation coefficient y comma x are all the same sign. They're either all positive or all negative, and this makes sense, considering one begets the other. The textbook also takes its time to remind us that these techniques are only applicable to linear relationships, and any other type of relationship will have to be corrected before undertaking any of the previous steps, whether through re-expressing or transforming the data, or taking some other rectifying or corrective measure. The least squares method is thus useful, but only after certain validations are made, and each property authenticated. We need to make sure it's linear, we need to make sure we have the right data, and so forth. Now, we've focused on calculating y up to this point, but there are also ways to test our hypothesis and to calculate the usefulness of x as a predictor, both informally and formally, as the textbook shows us. Informally, this can be found by examining the correlation coefficient and noticing the strength of the linear relationship between variables. More formal ways exist through calculating beta sub 1, where the epsilons are independent and random. There is a mean of 0 and a common variance of sigma squared. The respective variances of beta hat sub 0 and beta hat sub 1 are estimated using sigma squared, and can be found using predetermined values for your b sub 0 and b sub 1. We must estimate sigma squared, which can be found by taking the sum of squares of the residuals and dividing n minus 2, with n minus 2 also being known as the degrees of freedom. This is because it represents the number of instances minus the number of parameters. For example, a dataset with 100 instances, this means 100 x values and 100 y values. This would have a denominator of 98, because we must take into account the two parameters we have previously outlined, namely beta sub 0 and beta sub 1. This is where we test the null hypothesis, also written out as h sub 0, against the alternative hypothesis. The null hypothesis in this scenario is beta sub 1 equaling 0, and the alternative is b sub 1 not equaling 0. We want to test this because we know that if beta sub 1 equals 0, there is not a linear relationship, and this is the null hypothesis we have outlined. This is referred to as the t-test. The null hypothesis is rejected depending on the significance level, which we notate as alpha. The significance level is also framed as the level of the proportion that must be reached for a specific test value to be accepted. Also, we will talk about the p-value, which notates the probability of a random variable being greater than the absolute value of t sub 1. It is also the sum of the two shaded areas under a curve taken from computing t-distributions. When we have a standard bell curve, this will likely be the outer regions. We will reject it if the p-value of the absolute value of t sub 1 is less than or equal to alpha. Usually, p-values are simple to obtain, provided specific statistical packages, and this will help us on our journey towards finding the answer. There are also 3 alternative t-tests outside of the realms we have just touched on. The first generalizes to the null hypothesis, where b sub 1 is equal to b sub 1 exponent 0. This can be rejected depending on if a certain criterion holds, after the standard error is factored into the t-test. Using an appropriate number of degrees of freedom and appropriate critical values, we can ascertain whether or not a certain statistic is appropriate for both the sub-value and the exponent value. The second test uses beta sub 0 exponent 0. Note the sub 0, this is a difference. And the null hypothesis can be ascertained by subtracting this value from beta hat sub 0. Lastly, we can also use the correlation coefficient, which, by definition, whether or not y and x are linearly related. It tells whether or not y or x are linearly related, as we've previously discussed. Here, we measure rho equaling 0 against rho not equaling 0, with the null hypothesis indicating an equalization to 0, thus the graph being non-linearly related. Again, it could be any other type of expression, it just does not linear. So, to sum everything up, we have defined the situations where covariance is acceptable, correlation coefficients are acceptable, differentiated between the two, and regression analysis is acceptable, to add a wrench into that, and defined each situation where each one would be applicable and most desired. We have outlined the specificities that encompass regression analysis, including several parameters, the linearity of the line itself, the exclusion of outliers, and many other factors. We have ascertained multiple ways to dictate parameters and find how exactly to determine p-values. And we have also found a hypothesis that tells whether beta sub 0, the beginning parameter, is acceptable or not. This has been an outline of Chapter 2, Sections 1 through 6. Thank you for watching, and have a good day.